We're going to be reviewing the second unit of Physics 1, Mechanics, which is Newton's laws of motion and forces. Let's start off by reviewing Newton's laws of motion. The first law is about inertia, and a helpful way to think about this is in terms of the center of mass of a body or system. Now, if we are looking at like one particle, then of course our body is just a particle. But if we are looking at say a person on a boat, then this is a two-person system, so we can just consider this entire thing as a body. So Newton's first law states that that a body in motion will stay in motion, or a body at rest will stay at rest, unless acted upon by an outside external unbalanced force. So what this means is that the center mass, the position of the center mass, and the velocity of the center mass will remain unchanged unless there is an external net force on the system. So if our little guy here decides to walk to the left, he will exert a friction force on the boat, causing it to move to the left, but its center of mass will still be the same on an x-axis. Its velocity will also be the same. Why? With this guy moving to the right and the boat moving to the left, its net velocity will still be zero, confirming Newton's first law of inertia. Newton's second law is extremely important for its description of how things move kinematically with the net forces that act upon an object or a body. So we're going to have because these are vector components, we're going to have vector quantities, we're going to have vector components in the x, y, and z direction, or whatever coordinate system you choose. Now, the third law is often misinterpreted to mean that action-reaction pairs are between different forces, and this is not true. When you lean against a wall, I don't know, maybe you're waiting for something. You're exerting a force of the person onto the wall, and it will exert an equal and opposite, as given by this arrow, wall onto person force. This is Newton's third law. Newton's third law is not, as many understand it to be, a person standing on the ground with a weight and a normal force acting on them. These are not the same forces. They're not. The bottom is a force of gravity, and the normal force is a contact force. The person is exerting a normal force onto the ground he is standing on, as much as the ground is exerting a normal force back onto him. But this weight, what is its action-reaction pair? Every force has an equal and opposite force. So where is it acting on? Let's consider the fact that he is standing on planet Earth. He's this tiny little speck. He is much larger than he ought to be on this drawing. But I'm just showing this because if I write Newton's second law for each of these, let's consider that the mass of Earth is far, 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 far greater than that of the person. So, sorry, I forgot to write an A. This acceleration will also be, by comparison, extremely tiny because these forces are the same. Which means that this Earth, this planet, will not be noticeably accelerated to the person. Now, let's look at centripetal force and a Hill problem. Centripetal force is the net description of forces in the radial direction. The radial direction simply means that when we look at a circle, we are looking at any direction given outward. Now, you might be wondering to yourself, I thought that centripetal force was directed inward. And you're right, it is. Which is why we have this negative sign here. This negative sign means that it is opposite our orientation and is directed inward. So, let's take a Hill problem. I would like to look at this area and this area of our Hill problem. Here, we can imagine the center of our circle to be here. And we can look at the forces acting on, say, a cart. If the cart is here, then the forces acting on that cart in our little free body diagram are going to be the force of gravity and should not draw that there, should draw it where it's acting upon the normal force. So if we write our Newton's second law and we sum up all of the forces in the radial direction, well, let's remember that our radial direction is outward like this. Let's look at what forces are outward. We have normal force, and no more forces that are outward. What about the inward forces? Well, we do have the force of gravity, which will have a component in the radial direction. So because we're looking at this qualitatively and we're not going to actually solve for it, I will write minus Fg radial, which will equal our centripetal acceleration, MAC, which, I should write negative there because it's directed inward, which equals negative mv squared over r. So if I want to calculate the normal force, I can rearrange this to be Fgr minus mv squared over r. And this should make sense to us. If you've ever gone on a roller coaster, the normal force, or how much the seat is pushing up on you, will change depending on how fast you're going down that hill. The faster you go, we can see less normal force there is. Now, let's say you're in the center here. Your cart is like this. Your center for your circle is no longer here. Is no longer here. It will instead be here. So now the radial direction is going to be out this way. Now let's write our second Newton's second law and look at things in the radial direction again. Notice that the radial direction will change depending on where you are and in what circle we are considering. Here, we know that there is a normal force acting up and there is the force of gravity acting down. We are not writing centripetal force in our free body diagram because it is a net description of the forces, not necessarily a force unto itself. So let's write everything in the outward radial direction. We have the force of gravity, and we have nothing else outward. So let's look at the stuff inward. We have minus normal force, because it's directed inward, and that is about it. Now let's write our centripetal acceleration, minus mv squared over r, and let's rearrange for the normal force here. We can put n to this side, and the centripetal acceleration to this side, which gives us Fg plus mv squared over r. This should also follow intuition. When you get to the bottom of a hill like this, and you start to follow the path of the little valley here, you should feel an increased normal force from your seat. All right, that follows our intuition. So let's briefly look at an Atwood machine, just as an application of Newton's second law. We're going to have M1, M2 with gravity acting downward, and we are going to consider that M1 is going to be less than M2, which means that M1 will accelerate upwards with A1, and M2 will accelerate downwards with A2. Now we're going to consider the downward direction this time to be positive. All right, let's draw our free body diagram. M1 has two forces acting on it, M1G, and a tension. Let's see. Now, M2 will have two forces acting on it, M2G, and also tension. Interesting. Let's write the F equals MA for these. We are only concerned with the vertical direction. So let's look at our forces. Let's first consider M1. So we have the net forces. Let's consider everything that is in the direction of our orientation as assistive forces. So we have M1G as our assistive force. Do we have any other? I don't think we do. Now let's look at our resistive force. Sometimes you will hear these referred to as retarding forces. I will be referring to them as resistive forces. So let's write minus T. And let's write that these will equal M1A, or M1A1. Let's look at the second equation. M2G minus T equals M2A2. Now, because these are connected with the same wire, the same ideal string, we should take note that A1 is going to be, the magnitude of A1 will be equal to A2, but A1 will, according to this, because it's going to be accelerating upward, be negative. Why negative? Remember that we considered our downward direction to be positive, so let's be consistent. A2 will be greater than 0. So what we can write instead is that the magnitudes will equal A, and we can rewrite this as a little system of equations, minus T equals negative M1A, and this one as M2G minus T equals positive M2A2. All right. Oh, sorry, A. So let's rearrange again. So if we put tension on one side of the equation, see, yes, there we go. A tension equals M2G minus M2A. And now we can set the system of equations equal to each other. M1G plus M1A is going to be equal to M2G minus M2A. Okay, so if we're looking for acceleration, which is generally what Atwood questions ask you to do, we should isolate A. Let's rearrange everything so that A, our acceleration, the magnitude of our acceleration, is all on the left side. So we're going to have M1A plus M2A. Now let's move all of our G terms, our gravity terms, our weight terms really, to the right-hand side. So M1G plus M2G. Now, I made a sign error. It should be M2G minus M1G. And now we can factor out our A, M1 plus M2 equals, again, we can factor out our G, M2 minus M1. And we can get that the magnitude of our acceleration is going to be G M2 minus M1 over M1 plus M2. And all we did was apply Newton's second law and look at the forces acting on our system. However, there were other nuances here too. We kept in mind the orientation of our coordinate system. We looked at our initial conditions, and we used those with Newton's second law to solve this question. Last, I would like to explore how we are able to find the coefficient of friction of a flat surface with a little box on it using only the angle at which it is tilted. Now, I believe this may have been shown in class, but I think it is worth exploring again just to see how it was derived. So let's look at the forces. We have a normal force acting on the bottom of it, and we have let's say that the box has a mass m, and that this surface has a friction coefficient of mu naught s. So it's going to have a weight mg. So when we break this down, and let's consider this upward direction like this x, our positive x direction, this normal direction, our y direction. So when we look at our x direction, oh, I forgot to write a force. Oh my goodness. Okay, so had this friction not been here, this block would slide down. So to oppose it, there will be a force friction acting in our positive x direction. Apologies for that. So let's look at all of the forces in our positive x direction, which we have friction. Anything else? No, we do not. Minus all of the forces in the negative x direction. And here we have the component of gravity downward, or I guess the negative x direction, not necessarily downward, equals, is this object accelerating? No, it is not. 0. Let's check our y direction. So again, this is not going to be accelerating, so it's going to have a 0. We're going to look at everything in our positive, which is our normal force, and everything in our negative, which is mg cosine theta. So we're going to have n is going to be mg cosine theta. Now, because we're trying to find the coefficient of friction, we should look for the case where F is the maximum. The maximum friction force is given by the normal force times the coefficient of the static coefficient. The coefficient of friction. Static coefficient of friction, yes. So let's rearrange our x equation to be normal force times mu s minus mg sine theta. Let's rearrange again. N mu s equals mg sine theta. All right. So now we can take our normal force and plug this in here. Mg cosine theta mu s. If this looks familiar, then we are on the right track. We can take out our mg's, divide our theta terms, and get that mu s is going to be equal to sine theta over cosine theta. And again, this is just mu s equals tangent theta. These are two strong applications of Newton's second law, and keeping in mind the initial conditions with which we do them. I hope you found this helpful, and if you haven't done these problems along with me, I highly encourage you to watch again and do the same thing. Thank you.